All right. So as I was saying, I decided to change the direction of the course. I was going to end on the epilogue was supposed to be the ON model, but I decided I'm going to go over QED because for some of you guys are not going to take the course, and I part of the course, and I want you to have seen what a photon is. So review of lecture 24 that was left unfinished. We talked about the Yukawa theory, and we talked about the amplitude for a fermion anti-fermion scattering, this process, right? There were two Feynman diagrams that were contributing at this level, tree level. And here are the two Feynman diagrams, right? You recognize IG minus IG has to do with two of them, each has to do with a vertex. This is the propagator for the mode that propagates in the middle. This is P. Hopefully I'm going to get this right. K prime, P prime, right? Therefore, this is P minus P prime. And then this is P, K, K prime, P prime, right? So this is the propagator in this case. And you recall the notation for the external legs. This is what the amplitude was. Last time around, we squared the amplitude and sum over spins. The sum over spin was justified physically by the virtue of the fact that we said, well, if our detectors don't detect spin, we should sum over the probabilities for the processes. We did that, and the structure that we found from the calculation was trace of it was we repackaged the calculation, the essence of the calculation in terms of like a structure like this. You can see easily that here this is a 4-column vector, this is a row vector, so I've rearranged the two so we get a 4x4 matrix, and then hence the trace, right? Now we said that if you stare at this expression, what you see in it is there's a bunch of slashes. These are Q mu gamma mu's in the propagator for Q. There's also these guys, these propagators, right? And if you expand this expression, you're going to end up 4 types of terms. Terms with a single gamma matrix, terms with 2 gamma matrices, 3 gamma matrices, and 4 gamma matrices. We said that it follows from the Dirac algebra, that Clifford algebra or Dirac algebra, whatever we called it, that an odd number of trace of odd number of gamma matrices vanishes. So all you need to worry about is 2 and 4 gamma matrices, and these are the identities that follow from the Clifford algebra, right? But these are identities that help you actually do the calculations and simplify things. Now, something that I dropped last time, because I wasn't going to go towards QED, but I changed my mind, is that, so when you talk about the 2-to-2 scattering, it's plausible. You can think of 3 different processes. They don't always happen, right? If you have a 2-to-2 scattering, it's imaginable that some Feynman diagrams of these 3 types contribute, right? So convention is, this is called the S channel, this is called the T channel, and this is called the U channel. So this is just a standard convention. For example, if the external legs are scalar field, all 3 of them contribute, of course. Good. Well, it has to be a 5-5 psi theory, which is unstable. But anyway, so these are called this is just notation: S channel, T channel, U channel. All right. We talked about cross section. Cross section physically is the number of scattering events with fixed final states divided by the area of cross section, the area of collision, right? This area, the density of the beam A, the density of the beam B, and the width of the beams, right? So that's a process that this is a quantity that we call cross section. Just simply, it follows from the fact that if you look at this collision, this general set of collision, the total number of scatterings events will be proportional to rho A, rho B, LA, LB, and the area. Therefore, if you want to get an invariant, you just divide by it, you find something called cross section. We said its dimension is area. It has a dimensionality of area, L squared. We defined differential cross section because when you have a scattering event, the final states will fly off like with all sorts of different external momenta. So you could talk about the cross section for fixed values of final momenta, let's say P1 and Pn, because these external momenta are on shell. So it's sensible to what is sensible to do is to take the differential cross section to be d sigma dp1 purely to dpn. Hopefully you recall that these are what the definition of these guys were. These are the covariant, right? Then we talked about conservation laws, of course. Like for example, in 2-to-2 scattering, the number of free variables are basically two that you could use by, you could use the solid angle theta on 5 for the external legs from incoming, when you collide two particles, the center of mass, the outgoing particles, well, they're going to come in some direction. And of course, for conservation of momentum, all that you care about is just one of them. And that initial one and the initial collision axis. Yeah. So this is the center of mass collision, right? So this is angle theta, but of course this is three-dimensional, so it's theta on 5, right? And those are the two variables that we need to care about when we talk about the 2-to-2 scattering, just by counting of the degrees of freedom. Therefore, people often talk about the solid angle cross section, differential cross section. All right, I'm gonna go over this quickly because because we simply don't have enough time. We talked about this a little bit last time. If you have an unstable, you could have so far we have not talked about the phenomenon where the external leg, the incoming leg, is just a single particle. A single particle decaying to a bunch of other things. That will be decay, right? So a process that has one incoming and a bunch of outgoing, you would call that decay, you would not call that scattering. And such a thing would be associated with unstable particles. So this particle clearly cannot be on shell, because if it were on shell, this process would never happen. So we have to start talking about unstable particles. These unstable particles, as I said, they're intimately tied to resonances. But if you're interested, you will do some further readings. So the decay rate is the number of decays per unit time divided by the number of A particles present. So you could sit in the center of mass and say you have a tank of a bunch of, like unstable particles, and then they decay. Yeah. Have you heard of proton decay? The answer is they don't decay, but people prefer the tank, and they've been waiting for them to decay. All right. So the lifetime, if there are, a particle, an unstable particle can decay to all sorts of final results, and there will be a decay rate associated to every possible outcome. And so if you sum over all final outcomes, the inverse of that gives you a time scale that is called the lifetime. Good. Hopefully it's clear the dimensionality of how it works, right? It has dimension of time. Any questions? So this is what lifetime is. All right, a little bit of chat about resonances. I won't be able to do justice to this, but I just want to poke you guys a little bit to think about this. So we talked about particles that are on shell. The propagator is, depending on convention, 1 over p squared plus m squared plus I epsilon or something. Well, actually, let's not put that for now. So this is the propagator, and or my notation where there's minus. I think this is -1. This is +1 minus sign. And this is the propagator, and then we saw that if you look at the 2-point function of massive free fields, right, and you separate them by long times, the 2-point function at the long time limit, times much larger than inverse mass, will oscillate like e to the power of I mt. It will just oscillate. Now, if it were an unstable particle, the 2-point function would not oscillate, it would decay. So on top of that oscillation, there would be a decay rate. E to the power I m t minus gamma t, right? So that would be a way to model an unstable particle. Very good. So let's Fourier transform that, and you Fourier transform it. You get what you get. If you do things correctly and you generalize it properly to quantum field theory, I'm just jumping over a lot of stuff. You learn that the corresponding answer, way to model an unstable particle in quantum field theory, in relativistic invariant theory, is 1 over p squared minus m squared plus I m gamma. Good. All right. Good. So now this is the process that something decays to a bunch of other things, right? This is an amplitude. We're talking about an amplitude for such a thing. So what will be the cross section? The cross section, we haven't described we said the cross section is the amplitude squared times some kinematics, some geometry that I'm gonna quickly describe today. I'm gonna go over it really fast. I'm pointing to the section of Peskin because you have to get to photons, but here it's pretty clear that if cross section is proportional to m squared, then if gamma is not present, what do you expect in cross section? If you plot cross section as a function of energy, incoming energy, you get a pattern, but every time you go on shell, you have enough energy, you should get it will shoot up, right? It's a pole. It's a pole. So it will shoot up. But when you have an unstable particle, instead of a pole in your plot, what you will see is a bump. So there's some sort of you see a bump. And this bump is to be interpreted as an unstable particle. If you just plot this function squared is going to be, so this is that function. 1 over p squared minus m squared plus m squared gamma squared. If you plot that, you will see that it has a bump instead of a pole. And the width of the bump is controlled by the lifetime. That's actually how we discover particles in experiments. So we have a process. We look at some sort of like that's how we discover Higgs. We discover every single particle. We have a cross section for a process, and if there is a particle of a certain mass, as you vary the cross section, as you vary the energy, plot the cross section as a function of energy, you should see a bump, and the width of that bump will tell you about the lifetime of the particle. All right, I know this is quick, but I apologize. There's not much we could do. All right, any questions? All right, a little bit more about cross section and the description of the kinematics of it. Again, I'll go through this really fast, and there's a section of Peskin that I absolutely recommend you guys read it. It's not terribly crucial so that you could follow the rest of this the lectures, but I think it's an essential part of the story, understanding how to calculate that cross section starting from an amplitude. So that's what we want to calculate. Cross section starting from the amplitude, right? Cross sections are what we observe. Recall what cross section was. It was the number of events of a certain scattering process, right? Divided by the length of the beams and the density of the particles and the area. First of all, it's called in English, it's called cross section, but the area of the incident beams. All right, so imagine that you have you're colliding two things, A beams and B beams, right? So these beams are full of particles, right? And we're gonna model it, A being at rest and B is just coming in. So the initial state is some phi A phi B, and then we're gonna scatter these guys, and the outcomes are gonna be n different types of particles, right? 2n and out. The n particles that are going out are going to have momenta p1 to pn, of course, on shell. And what this if this is a probability for such a decay, it would be this amplitude squared integrated over over all the outgoing particles, all the outgoing momentum. Good. Let me skip this. All right. So the incoming thing is a wave packet, right? Because well, actually, this is I suggest that you guys derive this. So now I'm describing the pre-collision geometry, pre-collision state. The pre-collision state is the beam A. The particles are in some moment, has some momenta Ka. Particles of the sky have momenta Kb. These are some wave packets. They're on shell. You integrate over them. And now there is an impact parameter. It's pretty clear that impact parameter should play a role in any collision problem, right? So you put the impact parameter there, and you have to integrate. Good. This is the initial state. Let's pause here. I'm gonna ask you guys to derive this, but let's stare at this for a second to see if it's clear. All right. So that's your initial state. The final state, the probability is going to be the amplitude of the initial states, right? So this, let's look at this. So we have to take the overlap of this with P1 to P out. That this guy has Ka, Kb, all these factors come out. I'm gonna get Ka, Kb, overlap P1 to Pn squared. That's the amplitude. So here we go. These are the amplitudes, right? I have two sets of these because I'm integrating over, well, I'll have two sets of these, right? And these are the geometric factors that come out. The one that you want to pay attention to are these impact factors. So it's just nothing but putting the geometric description of initial states in there and keeping track of the impact parameter. If this is too quick, Peskin goes through this slower, but yeah. All right, so here's where I'm gonna make a jump. And basically section 4.5 of Peskin, what you do is you take this expression and just massage it, and you have to make a bunch of assumptions. But at the end of the day, what you end up with is, so maybe I should explain. So you here, the thing that you pay attention to is that you're gonna have conservation of momentum. So PF and KIs are going to be related. You're going to get Dirac delta function. So that Dirac delta function next to these guys will allow you to perform your integrals explicitly, right? That's what's in the that's what one set of them, right? Because you can perform integral over one set of these variables explicitly. You're going to be left with cross section as an integral over only final momenta, the amplitude squared over VA minus VB. Now I'm going to ask you guys to derive this. But yeah, the thing that you need to know about this is that hopefully this expression makes sense, or hopefully this expression makes sense. I just plugged in the geometric configuration of the initial wave packet in there, expanded. We used up conservation of energy momentum and wrote it this way. Oh, by the way, sorry, this is true only for 2-2 scattering. Also, we specialize 2-2 scattering. Is that right? No, 2-2n. Yeah, I think it's 2-2n scattering, but it has to be 2. Yeah, but here you see why I wrote it this way, right? Because what was the differential cross section? It was d sigma dpfs, right? So what sits in here is basically the differential cross section. So what you learn is just the amplitude squared divided by this factor that depends on the incoming velocities. But you can derive that. So Now, what this quick discussion that we're not going to have time to do justice to tells you is that this basically, if you look at the differential cross section, is this guy is going to be m squared divided by minus b. And the derivation of this is just a bunch of like integrations and geometric description of your beams, and you're integrating over conservation of momentum. Questions? Recall that when we wrote the S matrix, we wrote it as 1 plus IT. We saw that we observed that T has a conservation of momentum in front of it, so we took it out and called the rest of it M. That's why after I use of the integration conservation of energy momentum, I still have the M squared, right? So that's why we find M actually, starting from the S matrix. All right. Any questions? So once again, to repeat, M is to calculate M. What we had to do was there were your in states here, your out states here. This was an S matrix. There's a piece to this which is 1 plus I, conservation of energy momentum, multiplied by M. Right? This 1 has to do with basically no interaction, particle just propagating, and then this is conservation momentum that's always out there, and this is the non-trivial part of the scatter S matrix. All right, any questions? Okay, so we're going to change gears. From what we're going to do from now on until the end of the semester is we're going to build towards a particularly important theory called QED, quantum electrodynamics. The matter description of that theory is a bunch of Dirac fermions, and there's no scalar in there. There is a spin 1 massless mode. All right, so that's the description of it. Spin 1 massless mode called photon, and it's a gauge theory. Now, as I said last time, I explained what gauge theories are. These are theories that are really non-local. They have non-local, particularly some particular non-local observables, and we insist on local description, how we end up with the gauge redundancies. It doesn't matter for the purpose of this this part of the course. I assume all of you guys have seen. Did we go over electrodynamics as examples of local theories? Yeah. Okay, good. At least you've seen that. So Maxwell equations are here. These. If there's something that's unclear, ask. This is Maxwell equations that you learned in Jackson or wherever you learned it. Then you learned that there's a much better notation, writing things in terms of this antisymmetric 4x4 tensor, right? The field strength is called F0I is the electric field, and Fij is epsilon ijk magnetic field. This is a totally antisymmetric tensor, and A mu is the 4-vector potential. A 0 component. We often call it the what do we call it? Potential. Electrostatic potential. Yeah, scalar potential. And then this is the vector potential. Thank you. It's vector potential. All right. Written in this way, F mu nu is nothing but the anti-symmetrized del mu a nu minus del mu a mu. For those of you guys who are familiar with differential forms, this is a 1 form, and then this is just d of a. Well, I should write it this way. F is d of a. But anyway, All right, so what are the Maxwell equations? They're del mu f mu nu equal to j nu. J mu is a source, right? Of course, it's a 4-vector source. The zero component is the charge density, and the spatial component of it is the current density. Good. Now, an interesting observation is if you take a derivative with respect to del of this equation of motion, del nu of this, you're going to get del nu j nu, which is equal to 0. This is the conservation of current, Noether's theorem. Why is this 0? Do you know? Yeah, it's an antisymmetric tensor. The two derivatives are symmetric. We could just change the order, therefore it has to be 0. So the conservation of current is already is already like sort of implemented inside this equation. All right, any questions? Unfortunately, as I said, I don't have time to explain why this is a gauge theory, why this action. But I encourage you to read the last lecture notes, last year notes. All right, so this is a gauge theory, meaning what? It means that there's a redundancy. Never say gauge symmetry. There is no such a thing in nature called gauge symmetry. There's only gauge redundancy. It's old and incorrect language. So what is gauge transformation? If you send a mu to a mu minus del mu of any function, your arbitrary favorite function, nothing about the equations of motion will change, and nothing about the field change. This is just a redundancy of the description. There's no physical meaning associated with alpha. The origin of this is very interesting. It has to do with the fact that we have a theory that's not really truly local. It has some non-local degrees of freedom, but we love locality so much that we're willing to invent unphysical stuff to preserve locality, and that's what's happening. So those alphas are some fiducial, arbitrary, like unphysical stuff we have invented so that we can write down a local action. Otherwise, the theory will not be local. And then the fact that you invented these are made up things, you always have to, whatever you calculate, you have to make sure that the final answer is independent of alpha. So only the alpha independent stuff are physical. Yes.
In quantum mechanics,
yeah.
If I write the Hamiltonian, then this is, I mean, this scalar and the vector potentials, they show up in the Hamiltonian way. So, if I make a gauge transformation, I believe it adds an additional phase to psi, if psi is my wave function. So, that does change the representation, right? When I write it in representation theory.
So you were talking about the Arnold-Bohm effect. Because this is the stuff that I usually explain, and yeah, okay. So I'm gonna say a few things. The theory is non-local, meaning what? It has local data, local observables. What are the local observables? Electric fields, what else? Magnetic fields. So these are local observables. These are gauge invariant, of course, as they should be. They're physical observables. But the thing is, the theory has extra observables that could not be written in this form. What are those observables? Those observables are somewhat topological. So if you take a mu, integrate it along a loop, curve like this, right? And if you exponentiate this guy, this is an observable that's called Wilson loop. Of course, it's a function of the curve that you've integrated along. So, all right, there are new observables and gauge theory associated with these loops if they are topologically non-trivial. Meaning what? Meaning that you could not shrink this. When can you not shrink? If there is some sort of flux, magnetic flux, going through this, then this picks up a non-trivial value, and this is a physical observable that you could detect in the Harloff effect, right? So that's the story. The wave function, as you go around this, if there's some sort of topological obstruction, will pick up a phase. Those are observables of the theory that are absolutely non-local. It could not be written in a local form, and that is why we sort of introduced it. The theory didn't have these observables. We would have tried to describe everything in terms of. Good. What would be the Hamiltonian? What is the Hamiltonian in terms of E and B? Hamiltonian density. Half E squared plus B squared. Yeah.
Yes.
Yes, you may.
Basically, what do you mean going around obstacle? So like
Exactly, very good. So here's some sort of a beam, and here's a detector. You shoot particles, charged particles. One of them travels up here, the other one travels down here. They interfere by a certain, the phases are off, and how off they are, let's say they go around it, but the length of the curves are the same. And they still continue to interfere. That interference amount is related to this observation. That's how we detect it. Bowman effect. Aharonov-Bohm effect.
isn't that also what Manfred did with the alien aliens?
Probably. Yeah.
So I was curious about what it means to observe.
I think we talked about that with my I think that might be a little more general.
So
Yeah.
let me say that there is charge here. This is a super compact notation. So if you have fractional charge, you will see phases here that you wouldn't have expected. That's how you find fractional charge for sure. I don't know about the details of the experiments. They are probably going through fractional charge, so I imagine. That's why I said probably, but I do not know. I'm so much of a theorist that this morning I was teaching quantum mechanics, and I said that the diameter of a proton is an angstrom. I was off by 5 orders of magnitude. Just 5. It's the diameter of an atom, not a proton. All right. That's not a. It's not an excuse. It's pretty bad. All right. Good. All right. So what is the action? What's the Lagrangian density? The Lagrangian density is. Oh, by the way, F mu nu in this theory is gauge invariant. Just look at it. This matrix is made out of E's and B's, and they're gauge invariant. That's true for electromagnetism, not all gauge theories. Non-abelian gauge theories is not a true statement. Okay, but we don't care about those. It's beyond the scope of this part of the course. So this is gauge invariant, and the action is actually, as we said earlier, is half. The Hamiltonian is half E squared plus B squared, and this is what the action is: F mu nu contracted plus J mu A mu. Gauge invariance requires the conservation of charge, right? Because if you make a gauge transformation after so A mu goes to del mu alpha, you do an integration by parts, you put the del mu over J mu. Here's what you get: the total derivative, you take it to infinity, it drops out. The gauge invariance, the fact that, the gauge invariance requires this term to vanish. Conservation of charge. Let me say it a little bit differently. Let's say you did not know about these observables. Okay? What you knew about is only E and B. What you will struggle to do is you will struggle to couple, to source that theory. You will struggle to write down an action that is local in terms of E and B and has a source. You struggle to do that. You introduce A mu, and one consequence of the fact that you introduce these gauge degrees of freedom is that current has to be conserved. This is related to another theorem we did not discuss, but maybe I'll bring it back next time I teach. All right, good. So F mu nu was del mu A nu as this expression. Let's plug it in. Let's just put it back inside the Lagrangian density, and you get minus del mu A nu plus these terms. Is it clear why I put 1/4? So that I get 1/2 here, 1/2 here. Should I do that on the board? You might have wondered, so far we're always writing 1/2 side our action minus half del mu phi del mu phi. Here what you have is this, right? Del mu A mu, del mu A mu, del mu A mu. There are 4 terms. 2 of them will look like this after change of, and then 2 of them look like this, right? So the 2 will give you half this expression. Now, this is the term that we look at. You do an integration by parts on this. What do you find? Well, this del mu comes on here. You end up with G mu nu del squared, or eta mu nu, right? You do an integration by parts here. It brings it here. You get del squared minus del mu del nu. By the way, look, pay attention to the sign, right? This term is positive, whereas this term is negative. So after integration by parts, you get this total derivative that you're going to discard. But this is the form of the Lagrangian density. What is this to be compared with, or to? Is to be compared with this. So what you're staring at is, looks like the equation of motion. We also interpreted this operator a little bit differently. What was it? Inverse propagator. Right? So here you should be already thinking about the inverse of this operator being the propagator. What is this operator? This is, in momentum space, is p squared eta mu nu minus p mu p nu. Right? Is that operator invertible? It's not. It means that you have to gauge fix. This is the first place where you see it, right? All that I'm saying is that look at this operator, write in momentum space as a matrix. It's not an invertible operator. It has an eigenvalue 0 eigenvector. How do you invert it? If you have a matrix that has an eigenvalue 0, how do you invert it? You project out the 0 eigenvalue and you invert it, right? So it's of course only invertible on the where the domain of the eigenvalue is not 0. When the domain where the eigenvalue is not 0, so you have to project that. The projection is the gauge condition. Every time you gauge fix, that's what you're doing. You're applying a differential operator that projects out the zeros of those modes. So we'll describe that. There are a million different ways of doing this. No, not a million different ways. There are a couple of different ways of doing it. And this is the covariant way. We're going to do this if you have time at the end of this lecture. I'll do it covariantly using final diagrams. But I find it more instructive to do it first in canonical quantization. So we're going to do this in canonical quantization first, because there's a lesson to be learned over there. And then switch to, I think with the notations that I'm Writing this is a minus sign. Changed notation a million times, sorry. All right, is this point clear? Good. So it looks like this is the equation of motion. By the way, this is not surprising. This is just del nu f mu nu plus j mu is equal to 0. I think the sign is off. It should be minus, but anyway. A few things to pay attention to. First thing, what was our field? It was A0 that we called phi, and AI. Phi, they call it phi. First thing is that this term is non-dynamical. There is no dynamics associated with A0. How do you see that? Well, I explained there. It has no canonical conjugate momentum. Why? How do you define the canonical conjugate momentum? Let's say you have the Lagrangian density. So what was pi of phi or scalar field? D phi dot. Awesome. So if this guy, A naught, has a momentum, A naught, it should be del L del A naught. Right? What is that? You know the action. What is that term? It's 0. Can you tell why it's 0? A naught dot, sorry. Lagrange does not depend on A naught dot. Why? Because the Lagrangian is made out of F mu nu, which is antisymmetric. Antisymmetry does not allow for this term. There can't be such a term. It's antisymmetric. So for that reason, there is no conjugate momentum. It's not dynamic. It's a constraint. We're going to solve for it explicitly. All right. So that's 1 degree of freedom less. Your vectors seem to have 4 degrees of freedom. Right? A mu seem to have 4 degrees of freedom naively. But we knew that we made things up. So this is unphysical. First thing. There is one extra unphysical degree of freedom here as well. There are only 2 physical degrees of freedom. That extra thing has to do with the fact that this guy is not invertible. It has 1, 0. This guy is not invertible. It has one eigenvector 0 that has to be projected out. So the theory of massless spin 1 particle has only 2 degrees of freedom in 3 + 1 dimensions. The photon has only 2 degrees of freedom. What are they usually called? Polarizations. This becomes very explicit when you write everything in canonical quantization. But it's good to see it in canonical quantization, but I encourage you not to think in terms of canonical quantization. All right, so A naught has no dynamics. We'll deal with it in a second. So let's just forget about A naught for now. So we're now focused on only AI, right? The vector potential. It still has gauge degrees of freedom. There are various ways to fix the gauge. So there are 3 that I've listed here. This is a matter of choice. What do you like to use? There are the first 3 gauges that you see are linear. mu equals 0. That's a linear gauge. For example, the axial gauge, the temporal gauge is when you say some time-like vector and a mu is 0. That's like setting A0 equals 0. If you pick n mu to be just in the time direction, that's just saying set A0 to 0. But you could do it for any time-like vector. That's called temporal gauge. You could do it for any light cone gauge or axial gauge. These are a little bit different. These are setting the derivatives to spatial derivative 0 or the whatever that is called, del mu mu equals to 0. The Lorentz gauge and Coulomb gauge. You would not be surprised to hear that Coulomb gauge is something they've been using all along, because you learn electrostatic as if there's a separation between space and time. You're not worried about covariance, Lorentz invariance, but the Lorentz invariant choice that's neat is the Lorentz gauge. Any questions about these gauges, gauge choices? All right, so what we're gonna do is that we're gonna quantize electromagnetism in the Coulomb gauge. So Coulomb gauge is the more familiar one, this guy, right? That's what we're gonna do. So of course, I'm doing canonical quantization, right? So to impose Coulomb gauge, a nice way of doing it is by applying the following projection operator to AJ. This imposes the Coulomb gauge because you could see that if you take this operator and act with del I on it, it vanishes. Is it clear? In Fourier space, Coulomb gauge is KI/AI equals 0. Remember this. This is very, very crucial. This is very important. KI/AI equals 0. All right. And this projection I'm applying is basically multiplying AIK by this. It's pretty easy to see that if you multiply this with KJ, for example, you're going to get 0. What does this do? Ooh, sorry. There's a... No, that's good. That's good. What does this do? Do you have an intuitive way of thinking about this? It's very intuitive. So you have a vector A. Oh, that's a big vector. You have a vector A. You have another vector K. Your condition is that A and K have to be orthogonal. KIL has to be 0. So it says take A, subtract from it this. Right? So first term is delta ij, you subtract from it this projection. What remains is perpendicular. Or in the other direction. Right? So that operator, del ij minus ki kj over ki squared, is basically this. Remove this. That's all it is. Now, recall, why does this matter? When we did quantize scalar fields, we found the harmonic oscillator, a degree of freedom for every momentum. It's going to be similar here. For every momentum mode, AIK, we're going to have a harmonic oscillator. K is the direction of the propagation of this particle. It has to be orthogonal. A mu has to be orthogonal to the direction of propagation. Right? Only 2 degrees of freedom that are left. Right? It's a 3-dimensional vector. The orthogonal direction is just 2D. And AI has to be in that direction. That's called polarization. All right, so let's do that. Let's just plug in this condition inside the Lagrangian density. It's a one-liner. You see that your Lagrangian density looks like AI dot squared. That's good. AI is a dynamical field. Minus del J AI plus this term. And then you end up with these extra terms. Plus del IAJ, del JAI plus AI dot del I phi. Phi is the A0. Right? Plus these terms. If you do integration by parts, you can put this del J over this, if this term vanishes. you put this term over here, this term vanishes. So these two terms vanish by integration by parts. Good. You end up with this Lagrangian density, and this is the piece that's coming from the A0. Rho is the charge density, right? Good. What does this look like? Do you recognize this? There is no term in the Lagrangian that has time derivative of phi. Phi is A0. The only piece that term in the Lagrangian that depends on phi is del phi squared half or something minus rho phi. Good. This is a constraint. So, meaning what? Meaning that if you vary, you find the equations of motion for it. These are the equations of motion, right? This is a Poisson equation. This is a non-dynamical equation. You solve this. When you were doing electrostatic, that's what you were doing. You were not solving dynamical equations. You're just solving this equation. You don't need to put any boundary conditions or anything. That's the answer. Right? It's a unique solution. If far away the scalar field A0 is vanishes. So here we go. This is the answer for it. This is the charge density. You tell me the charge density, distribution of charge density in the world. I will solve for you that equation. I don't need any dynamics. I solve it and I plug it back inside the Lagrangian density. That's just a shift in Lagrangian density or energy, right? The contribution of electrostatic charges is just a shift to the Hamiltonian. That's all. You could calculate it. It does not play a role in the dynamics. It completely is non-dynamical. Good? Questions? This is the Coulomb piece of the potential. All right. Any questions? So what we're going to do is canonical quantization. Hopefully we'll have time for Feynman path integral as well. So in canonical quantization, here's our equation of motion. Your equation of motion is minus del squared of AI of x is, if this was not there, it would be ji of x. It would have looked like 3 independent degrees of, well, 4 independent scalars. So, but now this is there so that we impose the gauge constraint. When j is equal to 0, the solutions to this are this equation. Can you see what is going on? Let me write that. So set j equals 0, the equations of motion tell you that minus del squared of ai is equal to 0. Right? I is a charge is a spatial index. So it looks like the equations of motion tell you this. What equations of motion are these? It looks like 3 separate massless scalars. This looks like Klein-Gordon equation if it were massless. So what are the solutions to it? Plane waves, right? We did that before. It's an integral over dk purely. This is the form of 3 momenta on shell, right? And then in canonical quantization, you introduced an ak e to the power of ikx, right? And then ak dagger e to minus ikx, right? You would think that you will have 3 of them. So you would think that you would put an index I here. Except that as we just discussed, because of the gauge invariance, you only have 2 degrees of freedom. This you have to have the condition. On top of these, you should have the condition that ki ai is 0. You only have 2 degrees of freedom. What you're going to do is you're going to introduce a degree of freedom lambda polarization, which is plus or minus epsilon lambda here, lambda, epsilon lambda of k, k here. Now, there are various conventions to pick, but now the condition that this vector field satisfies the gauge condition tells you that k has to be orthogonal to the polarization vector, polarization vector, right? And some standard choices are the right-handed and left-handed polarizations. Here I'm assuming that k is in the z direction. For a photon that's propagating down the z direction, the polarization is in the xy plane, and the convention often is this. You could pick your favorite convention. These are the so-called right-handed and left-handed polarizations. All right, is the idea counting of the degrees of freedom what we were talking about? Is it clear? These are polarization 3 vectors. Spin 1 massless particle has 2 degrees of freedom. We saw this before when we were doing the representation theory of massless particles, right? We talked about the little group from massless modes. For spin 1, from that discussion, it's evident that it could have only 2 degrees of freedom. Go back and look, you'll find it. All right, so these guys form, as I said, they form an orthonormal basis for vectors that are projected by this. That's a fancy set of words to say that it's propagating the z direction. There's a 2-dimensional space, so you pick 2 orthogonal vectors in that direction. Of course, they're orthogonal, and then of course they sum up to the projection to the plane, xy plane. And then we have creation and annihilation operators for photons of different polarization and special momenta k. This is the description of the electromagnetic field, U1 gauge theory, in the Coulomb gauge. It's a full description of the quantized theory in the canonical quantization. Actually, I have a bunch of comments about Hamiltonian. Do I want to make these Hamiltonian comments? Yeah, I will make it. Any questions? That's what a photon is. As I said, the Hamiltonian, to find it, you have to take derivative with respect to lambda of ai dot. We already know that there is no conjugate momentum associated to a0. So this is the conjugate momenta. You write down the Hamiltonian in this term. This is what the Hamiltonian is. And then there's a piece that's coming from the Coulomb, from the a0 that decouples. It's just a shift in the Hamiltonian. The fact that now the canonical commutation relations between A and pi are going to be I delta 3, as you expect. But now there's this projection. You always have to project out unphysical degree of freedom. These modes cannot have a degree of freedom in the direction of propagation. Okay? That means that AI and A dagger satisfy the standard canonical commutation relations when omega is the norm of k as expected for massless mode. All right, I said this before, the Hamiltonian ends up being just a number operator. So the Hamiltonian becomes this: the number of photon of arbitrary spin times the corresponding frequency summed over all the photons or integrated over all the photons that exist. Should be concerned a little bit because it looks like the Hilbert space is uncountably infinite. I'm not going to comment on that. Those are the issues of the infrared divergence. And then there's a shift. That's a vacuum energy. The vacuum energy, of course, has the volume infinity, the IR divergence, but it is what it is. And then you end up with the Coulomb contribution. So the lesson is as follows. When you describe to me a bunch of electrostatic charges, let's say you have no magnetic field. What you have done in terms of QED, in terms of electrodynamics, is that you have shifted the potential, the vacuum energy, by a certain amount. You haven't done anything dynamic. The electrostatic charge, but once the charges start moving, that corresponds to J hat, J vector. So that's the source. That's a little bit different. Good. I don't know if this was a question for you guys. It was not a question for me when I learned about electrostatic, that electrostatic equations we're solving were non-dynamical. There were no time derivatives. At the time, I didn't quite understand. But anything that has to do with dynamics better have a time derivative. Otherwise, what are we describing? All right. Path integral formulation. I'm going to be quick here because it's just an equivalent way of doing it, covariant way of doing it. But I'm going to pause for questions first. All right. So what is the story? We are, as usual, in path integral, we're going to path integrate over all field configuration, A mu, keeping in mind that some of these configurations are made up, right? And the action is S naught of A0. S naught just means that I'm setting the, what does it mean? I don't know what it means. S naught is what it is. Minus 1/4 F mu squared plus J mu. Oh, it just means that there are no other charges that we track. All right, that's good. So we did this already, but now you could do it covariantly. We saw that this F mu squared term up to integration by parts could be written as K squared delta mu nu minus K mu K nu. A mu K, A nu minus K. That's just a Fourier transform of this term. That's it. There will be, after Fourier transform, you're going to end up with these two terms as well here. To perform the this path integral, what we did before was that we completed the square. That's how we calculated the partition function in the presence of source for a scalar field. Remember the propagator that we found? Here, that requires that we invert this guy. But this is not invertible. It has a 0 eigenvalue vector. This is the projector that we need. If we insert this projector, P mu nu, K mu, K nu is equal to 0. This is the eigenspace that has 0 eigenvalue. So the components of A mu along K mu are not in the subspace once you project them out, right? So P mu nu, K nu is 0, and K mu, J mu has to be also 0. They can't be a source for an unphysical degree of freedom. Questions? I know I did this fast, but it's pretty straightforward. It's just integration that's completing the square, and then you notice that there's a vector with 0 eigenvalue. Sorry, there's a subspace. Sorry. So it doesn't make sense to path integrate over these components. We this P mu nu projects a 4 vector in the subspace of orthogonal. That's orthogonal to Q. So what is reasonable to do is to replace J nu with the projected one, and after that you complete the square. You end up with this expression. Good. Now you wouldn't be surprised that this deserves to be called the propagator. So let me write it in the board. This whole thing stayed fully covariant. And this gauge has a name. Well, what did we call it? Called it the Lorentz gauge. So the result is to compare, remember for the scalar field, this was exp minus half integral xy jx jy delta of f x minus y, right? This was this, hopefully, if you recall. This is for the scalar field. And yeah, I'm not going to describe anymore, right? So this was k squared minus plus m squared. So for a gauge field, what we find is minus. Oh yeah, sorry. Yeah, this I can pull it out. It looks like this. I over 2. I'm writing it fully covariantly. Actually, let me write it this way. So compare with this, so I should do it this way. X minus y, j mu of x, f mu minus y, j mu of y, right? So this was then here I delta f, whoops, k ends up being p mu nu of k over k squared minus I epsilon plus I. So what does this tell you? It looks like, first, it looks like you have 4 different modes that are massless. But then you realize that, oh, you're projecting one of them out. That's 3. I encourage you to think about what happened to the other one. So this is a propagator for the photon. So now you have, this is the propagator for scalar. What was the propagator for fermion? What was this? Propagator for fermion. Dirac fermion. So you know the propagator for Dirac fermion for massless gauge field spin 1 photon, and the propagator for scale. We know everything we need to start talking about QED. Are there any questions? This is the propagator in Lorentz gauge. P mu nu, I repeat, is delta mu nu minus del mu divided by del squared. So it's covariant. Well, it's a covariant form. Any questions? Yeah.
Just curious, like that K square that corresponds to 3 massless modes or 4 massless modes? Should be 3, right? Because 5 is known as.
Yeah, that's one. Yeah, sure, of course. 3 and then you remove 1. Yeah, of course. Yeah.
When we were talking about scattering, we were talking about unstable particles as particles that decay from themselves into more.
Yeah.
And photon. I know there are processes by which one photon can be split into 2 or more photons. Is that decay? Or is that something totally different?
No, there is no there's no such a process. There's no such a process. what there is that an electron can scatter off of matter. A photon can scatter off of matter, electron, and then a bunch of photons can come out. So those processes you're talking about are called quantum optics. A photon is going through a mirror or something, that mirror or half mirror or split something, and that has a bunch of that's matter. So your scattering is between matter and photon. The end result is matter and a bunch of photons. A photon is stable particle.
But we have one photon.
Sure, this is okay. You could have a photon, a Dirac fermion, and then this goes along, and a whole bunch of other ones come out. It's perfectly fine. These are Feynman diagrams, they're allowed. So in QED, we're going to see that we're going to have a vertex like this between the fermion and photon. And these are all allowed. As a matter of fact, you could have a fermion going along and just photon. Or you could absorb a fermion to just absorb it. These are all allowed processes. QED. But you need matter. Like the initial state cannot be just a single photon. Importantly, photons cannot self-interact. So if you write down the the Feynman rules, we're going to write them down later. But all that you have is this interaction, which is electron and photon interact, propagator for electron, propagator for photon. That's it. Electrons don't self-interact, photons don't self-interact. If photons self-interacted, we don't have classical reality. Think about that. This is fascinating. If photons self-interacted, you would have no way of performing measurement and having results that match. If you did a measurement, I did a measurement, a quantum system, it won't match. The fact that photons don't self-interact means that they interact with this, record the state of this, propagate all the way to me, and I see them, and along the way, they're perfect messengers. If we didn't have a massless mode like photon, we wouldn't have had the notion of classical reality. Anyway, yeah.
You say that electrons don't self-interact?
Electrons don't, in QED there is no vertex. Yeah.
So do we have to go beyond QED to explain things like Cooper curves? Or is that, again, totally different?
Those are, yeah, your theories are a little bit more complicated. Those are, first of all, okay, what's a Cooper curve? It's a bound state. So it's a quasi-particle. So we have a theory that the matter content of it has a whole bunch of stuff. You flew towards the infrared. Well, we haven't learned about normalization. The theory is strongly coupled. The theory is strongly coupled. Deep in the infrared, you end up with a bunch of collective degrees of freedom that do not like the UV degrees of freedom. These are quasi-particles. As we saw, like in the, there's no particular reason that the low energy theory looks like the lower degrees of freedom are like the UV degrees of freedom. So yeah, Cooper curves are like low energy degrees of freedom. There's an effective field theory that describes that. There's the UV theory that's described in terms of fermions and other craft that interact. Yeah. That's a very question. Yeah, those are mesons. Maybe you don't even have to go that far. Mesons are quasi-particles. All right, any other questions? Now, one little thing. I just said fermions don't self-interact. But can you draw a diagram where the ingoing legs are 4 fermions and in the middle that looks like self-interaction? So of course you can, right? You could have this diagram. You scatter photon, right? Now, in this example, photon is massless, so you will never confuse this. But there are theories where there are fermions and they interact through a massive particle, unstable particle. And if that particle is very, very massive and you're a low energy observer, your measurement devices, your detectors are not strong enough to resolve this particle. What you effectively see is an interaction. There was a very heavy particle that mediated this interaction, but because you're a low energy observer, you don't really know, so you think there's a self-interaction. So the low energy Lagrangian, the high energy Lagrangian may not be the same. Of course not, right?
What will be that particle? Do you know QED diagram for such particles?
Sorry, which one?
I mean, if you're speaking of a massive particle instead
No,
of
no, the QD, this never happens. This is massless. QD is massless, but there are theories where there's a massive mediating field, and then from the point of low energy, you can't resolve it, and you think it's an interaction.
massive to lose the information.
I'm not sure what you mean by that. If it's massive, the example would be SU2 gauge theory. W and Z bosons. Yeah, W and Z bosons. I haven't taught the normalization. This term is non-normalizable. It comes up in the UIR. Anyway. All right, any last questions? If not, thanks so much, guys.